In this video, we will study how data structures can reduce the amount of memory needed in running a program. We will use sparse arrays as examples. Sparse array is an array with most entries are 0, like this one. There are 12 elements, but only 3 of them are non-zero. If the normal array structure that is available in most programming languages is used to store this array, the amount of space needed is proportional to the size of the array. The time to access a particular array element using the index is constant. When the array is sparse and is very large, most of the space will be used for keeping 0, which is not space efficient as the zeros are not providing information. To store non-zero array elements in a space-efficient manner, we can use a linked list that links the non-zero elements together as shown. Each node in the list carries the array index and the element value. The nodes are arranged in the order of indexes from small to large. In this example, there are only 3 nodes in the list. The space needed for this linked list implementation is related to the number of non-zero elements. If the array is sparse, this representation can save a lot of space. However, we are not done yet. When we use a new internal representation to store a structure, we have to provide the standard operations for manipulating the structure. In our array example, accessing an array element is a standard operation. When a linked list is used to store the array, when user wants to read the array element of index I, we have to traverse the list from the beginning. If the required element is non-zero, a node will be in the list. If the node does not exist, the element being requested is 0. The time complexity is no longer constant, but is related to the size of the list, which is the number of non-zero elements. That is, although we save some space in keeping the array, we may have to spend more time in some of the operations. This is called time-space trade-off. In using a new representation, sometimes we may need to implement additional operations for manipulating the data structure more efficiently. Let's now look at the operation of finding the largest element in the array. When the transitional array is used, each element is visited once to locate the largest value, like the one here. The time complexity of this loop is big O of size of the array. Suppose the get method is implemented as discussed before to access the array element at index I when the linked list is used. We can use the name loop structure to identify the largest element. However, this implementation is very expensive, as for every array element access, we have to traverse the list once. If we do not have to stick with the implementation of the normal array, we can find the largest element very efficiently by traversing the list once. It takes only big O of number of non-zero elements time, which is smaller than big O of size. This slide shows the time complexities of some array operations. Normal array allows very efficient element access, but may be more expensive in operations that require array traversal. Whether the runtime of an application can be reduced by using the linked list implementation will thus depend on what operations are needed in the application. Next, we study sparse 2D arrays or sparse matrices. Given a 2D array of m rows and n columns, we need big O of m times n space to store it in a normal way. There are several ways to store sparse 2D arrays in a memory-efficient manner. The first one is by an array of linked lists as shown. A list, which may be empty, is maintained for each row. Each node carries the column index and the element value. The space needed is big O of m plus big O of number of elements. This representation allows rows to be traversed easily, but column traversal is not trivial. If both column and row traversals are needed often, we can link the nodes to both dimensions as shown. Each node now carries both the row and column indexes together with the element value. In this array of lists implementation, the space needed is related to the dimension of the array. It is in fact possible to further reduce the space needed to represent a sparse 2D array. In this implementation, the arrays of rows and columns are now linked lists. The space needed no longer depends on the array dimension. However, accessing a particular row or column takes longer time. It is another example of time-space trade-off. This concludes our discussion on sparse arrays.